Good morning, everyone. I hope you're doing well. Just a few reminders. So today we're gonna finish up set 3, rectilinear motion. We might not do all the problems, but you should be able to finish, like after this lecture, you should be able to complete sets 1 to 4. And please do that. Don't let the sets, accumulate. You need to be able to finish them quickly, and we're moving on and doing other sets next week and so on. Also, homework 1 is already posted and it's gonna be due. So usually the homeworks are gonna be posted on Thursdays and gonna be due the next Thursday. Next Thursday is off, so I made it due on Friday at the end of the day. I might change a little bit of the structure of the homework to make the deliverables clearer, but the questions are gonna be the same. If I do that, I'll do it this afternoon. Okay, so homework 1, and we're gonna introduce what homework 1 is gonna talk about. That's gonna be due next Friday. Homework is gonna usually be due on Thursday, except that next Thursday is off. Okay, any questions, any logistical questions or other questions before we start? Okay, cool. So last time we stopped at rectilinear motion, and I know you might have solved, did you solve any problems from set 3 in the exercise session yesterday? Yeah, so you did an example, but I still want to continue deriving this equation I told you about, and then we'll move on to a new topic. Okay, so we considered rectilinear motion, which is a motion along a straight line, and in this case I just aligned Ex with the rectilinear motion. So the position vector to the particle is variable along Ex, but it has a constant Ey component. Does that make sense? So you can think of the position vector as being the Xex vector plus the Cey. Then these two sum to R, and the Xex vector is varying, whereas throughout this motion the Cey vector is constant. And we can take the derivative of the position vector to find the vector, and the derivative again to find the acceleration vector. Okay, great. And we can recall, the relationships between velocity and position. V is dr by dt. Now in rectilinear motion, we can write this equation as a scalar equation. So V, I can write it as V is equal to dx by dt, just by projecting this equation along Ex. We'll do it step by step. I will replace V by Vex, and I will replace R by Xex plus Yey, or plus Cey, over dt. Are you with me so far? Okay. And then Ex and Ey are constants. D of this constant is going to be 0. This is going to go away. Here I'm going to be left with dx Ex over dt. Is that fine? Any questions? And then I can project this equation along Ex. What do I mean by projecting this equation along Ex? It's basically taking the dot product. I'll take the dot product of every term of this equation with Ex. So Vex dot Ex is equal to dx by dt Ex dot Ex. And who can remind us what x dot Ex? 1, exactly. So 1, 1, these go away, and we're left with V is dx by dt. So this projection is quite trivial, actually. However, in this class, we're going to use projections a lot, and they might be non-trivial because we're going to have a vector equation, and it's going to have components, vectors expressed along different bases. So we're going to project, an equation along Ex that has components along Er and Theta and so on. We're going to learn about this, but the point for now is that projections are very important, and projections are just taking a dot product of every term in the equation with the direction you're projecting about. Does that make sense a little bit? Yeah? Okay, cool. So V is dx by dt, and I can also write the scalar version of A is equal to dv by dt for rectilinear motion. A is going to be dv by dt. Okay. And now I'm going to do a small trick with this equation. I'm going to use the chain rule. I'm going to write dv by dt as dv by dx, dx by dt. That's the chain rule. So basically what we've assumed so far is that the velocity is a function of time. Now to be able to use the chain rule, what I'm saying is that the velocity can be written as a function of x that is then a function of time. So basically I can write x as a function of time. We don't have to go through this, or we might not right now go into the mathematical rigor of this, but if I can write function, this means that, does anyone know what this means in math? If I have basically y as a function of x, in which case can I write f as a function of y? There's a keyword here. Maybe I'll help you a little bit. What am I doing? Inverting. I'm taking the inverse of the function. And in what? Yes.
It's like 1 to 1.
Exactly. It fits 1 to 1. For every x, I have a unique time, and for every time I have a unique x, I can invert. And I can write velocity as a function of x instead of velocity as a function of time directly. So if I can do that, then I can invert and I can write v as a function of x, and I can use the chain rule. Does that make sense? Raise your hand if that's all right, kind of. Cool. Questions? Okay. Now dx by dt, you might recognize this term. What is it? It's on the board somewhere. Exactly, it's our v. Okay, so what I have so far is a is equal to dv by dx times v, which I can rearrange as a dx is equal to v dv. Okay. Maybe you've used this equation before. What it does is it relates the position, the velocity, and the acceleration without relying on time. So relates x, v, and a without explicitly relying on time. Okay. For example, in the first problem set 3 problem that you solved yesterday, let us check it. I have a few copies of these sets if anyone wants them. Set 3. Okay, so looking at set 3 from yesterday, if I look at problem 1, I have the acceleration. The acceleration is given in terms of what? A particle moving along a straight line has an acceleration which varies according to position, according to x. And if the velocity of the particle is given, we want to determine the velocity at a certain position. So we're given the acceleration as a function of position, and we want to determine the velocity as a function of position. So that would be a good problem to use this equation. A is given as a function of x. So if I plug in a as a function of x here, I can just integrate this equation and solve for x as a function of velocity. Do we see that? Right? So this is already a differential equation where all the x variables are on one side and all the v variables are in the other side. So I can integrate from x0 to x at time t. I'll make these dummy variables, v at t0 to v at any time t. Make these dummy variables. What's the integral of this side? V dv. the same as integral of x dx. Exactly, v squared over 2. Between v0 and v at time t. So that's v of t squared over 2 minus v0 of t squared over 2. Now to integrate this side, I'll need to know a as a function of x explicitly. Any questions? Okay. Take a minute, read problem 2, and then let me know what a is given as a function of and how can we solve that problem. So take a minute and read question 2 and try to think about a way to solve it. Okay, let us read this together. A 23,000 pound space shuttle orbiter touches down at 220 miles per hour. At 200 miles per hour, its drag parachute deploys. At 35 miles per hour, the chute is jettisoned from the orbiter. If the deceleration in feet per second squared during the time that the chute is deployed is given, it's minus 0.0003 v squared, where v is in feet per second. Determine the corresponding distance traveled by the orbiter. Assume no braking from its wheel brakes. So at 200 miles per hour, the drag chute is deployed. And at 35 miles per hour, it's jettisoned, it's removed. And we're given the acceleration as a function of what during that time? Velocity, right. So this is what's happening. At this point here, the velocity is 200 miles per hour. The speed is 200 miles per hour. At this point, the speed is 35 miles per hour. And in between, I have the acceleration being minus 0.0003 v squared. And we want to find the distance traveled. Delta x or d, I want to find this distance traveled between these 2 points. Guess which equation we're going to use? Exactly, a dx is equal to v dv. Why exactly here? Because we're given the acceleration as a function of velocity. We want to find the distance traveled. Time is not explicitly asked for. So let's try this. We have a dx and I'm going to replace a by its value, minus 0.0003 v squared dx is equal to v dv. Okay, cool. That's a differential equation now. How do I solve it? Can I just integrate both sides? Raise your hand if you think I can just integrate both sides. Raise your hand if you think I cannot do that. Discuss with your neighbors. Try to think about it. Can I just integrate both sides, or If you think you can do that, try and do it, see what happens. If not, what should I do? Okay, can I just integrate both sides? Can I integrate both sides? No. Why? Because here I have, well, v and then I have a dx. I cannot integrate v dx. Not straightforward, not in a straightforward manner, not v squared dx. So what should I do? Divide by v squared. So what am I basically doing? Exactly, I'm separating the variables. I'm going to put all the v squared variables on one side and all the x variables on the other side. This is a separable differential equation, so I can do that. And then I can solve it easily just by integrating it. So I'll get v and the v cancel out, so I'll get dv over v and then minus 0.0003 dx. Okay, cool. Now I can integrate. I'm going to integrate from x is 0 to delta x from v being 35 miles per hour. I'm going to have to convert this to feet per second times 5280 over 3600 and then 200 times 5280 over 3600. We have 5,280 miles 80 feet in every mile. And what's the integral of dv over v? Yes, ln v. Ln absolute value of v, but here the boundary. Ln absolute value of v, evaluated at the boundary, so basically ln 200 over 35. That's on this side. On the other side, I'll get the minus 0.0003 delta x, and I can calculate delta x, the distance traveled between the two, or while the parachute is up there, is deployed. Any questions? Yes. So I'm integrating, oh, actually, you're right. I should switch. I'm integrating from t0, where the velocity is 200. So initially, the velocity is 200, and then the velocity is 35. Okay, that's better. Now I'll get a 35 over 200. Ln of a number that's less than 1 is negative, and I have a minus sign, so I got a positive delta x. That makes sense. Okay, great, thank you. Any other questions? Okay. Problem 3, I'll let you solve on your own, but I'll just discuss it a little bit. In that problem, the acceleration is given as a function of time. So when the acceleration is given as a function of time, usually it does not make sense to use that equation, a dx is v dv. What we'll do for that is we'll just say that a is equal to dv by dt, and I can integrate v. And I can just integrate that equation to find the velocity. And I can integrate another time to find the position as a function of time. Okay? So please solve that problem and let us know on ad or during office hours or the exercise session if you have any questions. Deal? Cool. So now we're moving on to our next topic. The kinetics. We're going to start talking about forces. Linear momentum. We're going to define the linear momentum of a particle to be g the linear momentum of the particle of mass m traveling with a velocity v is g is equal to mv. So for any object, say this chalk, its linear momentum is its mass. So I'm assuming that it's a particle, basically has one velocity. Its linear momentum is its mass times its velocity. And I can calculate the rate of change of linear momentum. The time rate of change of linear momentum is g dot. How can I calculate the derivative of g dot? What will I get? If I have a certain system and I want to calculate the rate of change of its angular momentum, what would that be? MA, but you're making an assumption when you say MA. Yes. MV dot, that's the same as MA, but you're still making an assumption there. Yes. Exactly. So your friend is not making that assumption. What was the assumption? That mass is constant. But for a system, mass doesn't have to be constant. And when mass is not constant, we have to take its derivative. V dot is A. Can you think of systems where mass is not constant? Yes. Yeah, if something is, the system is some moving tank or some tank and the water is leaking out. If you have a rocket, for example, that's losing a lot of rocket fuel during its motion, that's a system where mass is not conserved. Now, for most of the systems, we're going to consider mass is going to be conserved. But in general, it doesn't have to be. So if mass is conserved, then we have G dot is equal to mv dot, which is ma. Cool. Now, according to Newton, Newton's second law, I'm going to refer to that as Newton 2, or Euler's first law. So Euler was the person who actually first wrote down Newton's laws mathematically. They had to invent calculus for that, derivatives. So he wrote Newton's first law mathematically, and not only for particles, but he also extended it for rigid bodies. And he added another law, another balance law, which we're going to learn about later on in the semester. Euler's first law, these are equivalent, or the balance of linear momentum. All three names denote this principle that F is equal to G dot. The sum of the external forces acting on the system is equal to the rate of change of its linear momentum. This could be also denoted as the net external force acting on the system. That's F. This is important because now we can relate the forces acting on a system to its motion. So this is basically a differential equation for the motion of the system, a vector differential equation. In which case would the linear momentum of a system be conserved? Yes. Exactly. When there aren't any forces acting on the system, when F is equal to 0, okay, this means that G dot is equal to 0 from the balance law. So G is constant. It's a constant vector. So the linear momentum of the system would be conserved if the sum of forces acting on it is 0. And that's basically Newton's, which law of Newton is that? Talks about conservation of linear momentum. If an object is at rest, it's going to stay at rest. If it's moving in a certain way, it's going to tend to remain moving in the same way. That's Newton's first law. What is Newton's third law? No, that's Newton's second law. Yes. Exactly. Newton's 3. For every action, you have an equal and opposite reaction. We're going to be using that law too. Any questions? Awesome. So let's introduce our coordinates now. In Cartesian coordinates, what was the expression of the acceleration vector? If I have Cartesian coordinates, if the base is Ex, Ey, Ez, what's my expression for the acceleration vector? That's supposed to be an easy question. Right? Or x double dot Ex plus x double dot, plus y double dot Ey plus z double dot Ez. Okay, and I can also write the sum of forces F in that Cartesian basis. Okay, and now I can write F equals ma. That's Newton's second law, assuming that mass is constant. So I'll get Fx. Or actually, let me write the second form. Okay. So this is a vector equation. And what dimensions? 3D, right? How many scalar equations can I get out of it? 3, exactly. How?
Balance each variable.
Exactly. In other words, we're going to call them projections, right? We're going to project this equation. I can project it along 3 independent directions, Ex, Ey, Ez, and I can get 3 scalar equations from that. So this is how I'm going to denote projections. Dot Ex, meaning I'm projecting this equation along Ex. I'm taking the dot product of every term with Ex. What will I get? Think about it, chat with your neighbors. What will I get if I project this equation along Ex? And then along Ey and along Ez? Chat with your neighbor, write them down. Projections are going to be very important. Okay, so I think you've got it. Fx is equal to mx double dot. Raise your hand if you agree. Cool. And then Fy is equal to my double dot. Fz is equal to mz double dot. Again, trivial now. Projections are not going to be trivial all the time. Okay. So what are these 3 equations? These are 3 differential equations. DEs, differential equations. For these 3 variables, x, y, and z. So if we solve these differential equations, we can solve for the motion. These differential equations are what we call the equations of motion. We can call this the equation of motion, or we can call this set equivalently the equations of motion. So in dynamics, our basic job is to get the equations of motion of a system, and then we can solve them. In this class, we're going to do simple differential equations that a lot of times we can solve by hand, but a lot of the times, most of the times, we cannot solve these differential equations by hand. We cannot solve all differential equations analytically. We might resort to numerical methods to solve them. That's what you're going to do in homework 1. You're going to use a numerical solver to solve a differential equation that we cannot solve by hand. Now, it might also, equations of motion can get a little bit more complicated when we add constraints to them. For example, if a ball is bouncing on a table and it cannot penetrate a table, that's a constraint that you're going to have to solve with the differential equation. We'll talk more about this throughout the semester. But now we know what an equation of motion is. A lot of times in the quizzes, in the homework, I'm going to ask you, get the equation of motion for a certain system. And that's what you're going to have to do. You're going to have to figure out what the degrees of freedom for the system is, and you're going to get a differential equation. Basically, as many differential equations as there are degrees of freedom. We'll do more of that. Let's start with an example. Our first example. The simplest one, you've probably seen this before, projectile motion. So what we're going to do is we're going to consider a certain projectile. So consider a mass m. Actually, what I'm going to do is I'm going to start this example on the other board over there. Okay. Okay, so we're going to consider a simple projectile, a mass m, a particle of mass m, and that projectile is launched with an initial velocity v0. And we have gravity pointing downwards. I'm going to add an origin. I'm going to take O to be the origin at the initial location of the mass m where it's launched. I'm going to take my Ex and Ey Cartesian basis. In this case, where does Ez point? Outside the page or inside the page? What? Raise your hand for outside. Raise your hand for inside. We'll discuss. We have not a consensus. Okay, let's see. Do we have a consensus? Raise your hand for outside the page. Raise your hand for inside the page. Well, raise your hand for outside the page again. Is it high? Okay, raise your hand if you're undecided. Well, yeah. What is Ez equal to, first of all? Ez is equal to what? It's the cross product of which two vectors and in which order? Ex cross Ey. That's what makes Ex, Ey is a right-handed basis. That's a right-handed basis. So this cross this is equal to this. And we can go in circle 2. Ey cross Ez is Ex and so on. So I determine the direction of the cross product from the right-hand rule. So I can take my right hand. Usually it's the hand to write with, but I'm left-handed, which is the one lucky instant for being left-handed. Okay, Ex cross Ey. Your fingers, you curl them from Ex to Ey, and your thumb points along Ez. Okay, Ex cross Ey is Ez. So Ez is outside the page. Really, we don't really need to worry about Ez in this problem. You're going to see that what is the acceleration along Ez is going to be? 0, because the sum of forces along Ez is going to be 0. But we'll get to that. be sure about something. We won't assume we're going to derive things step by step. Okay. So when we're solving a problem, I'm going to write down the 4 steps in a bit, but the first step is going to be what we did now. We chose our origin, we chose our basis, and I'm going to write the position vector also to the particle. So in general, I can write the position vector to the particle in the chosen basis as R is equal to xex plus yey, right? And then V as x dot ex plus y dot ey. A as x double dot ex plus y double dot ey. That is step 1. Step 2, we're going to draw the free body diagram of the particle. So to draw the free body diagram of our system, we need to choose what our system is. What is our system in this problem? What is our system that we're solving for the motion of? We're solving for the motion of the particle, so we're just going to consider the particle, and we will draw the particle isolated on its own. What are the forces acting on this particle? We have, well, the weight force. The weight force due to gravity is acting on the particle. Any other forces? We could have drag from air and so on. For now, we're going to assume there's no drag, and then we're going to add on drag later on. Okay, so assuming that there's only the weight force acting on the particle, the weight force is equal to what? Mass times gravity, or minus mg ey. Okay, so this is what we're going to do for free body diagrams from now on. We're going to take our system, draw it, isolate it on its own, and then draw the forces acting on it. And then on the side, if we know what the expression of the force is, we will write it. Okay, so for example, if I have a box sitting on a surface and gravity is acting like this, how do I draw the free body diagram of the box? Well, first I'll draw the box on its own without the surface, right? Isolate the system, and then I'll draw how many forces are acting on the box? 2, the weight and the normal. And the weight is equal to minus mg ey, and the normal is equal to n ey. Do I know what the magnitude of the normal force is? What is it? mg. Why? Where did you get that? Newton's third law? Newton's second law, I would say. But that's only true if the surface is not accelerating. If the surface is accelerating, what would the normal force be? What equation would you have to use? If you want to find the equation of motion of a block, what equation would you use? F equals ma, Newton's second law. Okay, we will get to that. Okay, for now, going back to our projectile, I have the free body diagram. Now I'll do step 3, and I'll write the balance law. Very important. I'll write the vector equation for the balance law. F is the sum of forces, so I'll copy all the forces from my free body diagram. Minus mg ey and ma is equal to ma. And that's my equation of motion. That's a vector equation in 2 dimensions. So how many scalar equations can I get out of it? Raise your hand for 1. Raise your hand for 2. Raise your hand for 3. Convince your neighbor of what the answer is. How many scalar equations can I get out of this vector equation? Okay, so what's the consensus? Is it 1? Raise your hand for 1. Raise your hand for 2. Okay, you still don't have a consensus. Raise your hand for 3. Okay, convince your neighbors again. Obviously, someone is not making good enough convincing argument. So, what do you think? How many scalar equations can I get out of this? Only one? What do you guys think? Equations can I get out of this? How do you get one scalar equation? Projecting along which direction? So how would I obtain the scalar equations from this vector equation? Yeah, dot product, projections. So if I project along Ex, I'll get a scalar equation, right? And if I project along Ey, will I get another scalar equation? Yeah, so how many scalar equations can I get? 2. You could even say 3. If I project along Ez, I'll get a scalar equation along Z. Okay? So I can project along Ey. Well, or along Ex, what will I get? What will I get from this side if I project along Ex? 0. And what about the other side? Recall the expression for A. So what will I get? On this side, what will I get if I project along Ex? X double dot. And what about if I project along Ey? On this side, what will I get? Minus mg is equal to m y double dot. So that's 2 scalar equations, which you can integrate to find the equations, to solve for the motion, x of t and y of t. So these you can actually integrate by hand. Yes? Sure. So this is the equation I have, right? Minus mg Ey is equal to ma. A is x double dot Ex plus y double dot Ey, right? So if I take the dot product of every term in this equation with Ex, what is this term dotted with Ex equal to? What is Ey dot Ex? 0. Why? They're perpendicular, right? We discussed that on Tuesday. That's why it's very important to study day by day, right, guys? Especially the people shaking their head like this. Okay, so it's 0. And again here, what is Ex dot Ex? So what is this term dotted with Ex? 1. So I'll get mx double dot. What about the Ey term dotted with Ex? It's again 0. So I'll get 0 is equal to mx double dot. That's the first equation. Does that make sense? Yeah, the initial velocity is along Ex and Ey. Okay? Okay, that's my equation of motion I can solve. I can solve for the position vector as a function of time. This is an easy differential equation to solve. Okay, so where was it? MA or A, I'm going to cancel the mass on both sides. A is equal to minus G Ey, and A is equal to dV by dt. So dV is equal to minus G Ey dt. Can I integrate both sides of this equation? Yep, why not? So integrating from V0 to V at any time t integrating from t0 to any time t. What will I get on this side? Don't let the vectors bother you. It's the same as you would do for a regular integral. So what would that be? Right, v of t minus v initially at t equals to 0. And on this side, I'm just integrating. Ey is a scalar, and minus g, sorry, ey is a constant. And minus g is also a constant. I can take minus g ey outside, integrate from 0 to t dt. So that will be minus g ey at t. Does that make sense? So now I have that v of t is equal to v0 minus g ey times t. That's the velocity of the particle as a function of time. Okay? And I can integrate one more time to solve for the position vector as a function of time. Actually, I'll let you do it. Go ahead. Solve for the position vector as a function of time. You can chat with your neighbor if you need to. Solve for odd the position vector as a function of time. Go ahead. Maybe a couple minutes to do that. You need to be underlining vectors. That's a vector v, needs to be underlined, v0 also. Okay, all the vectors you need to underline. What's up? Oops. So we're starting with V is equal to dr by dt. So R dr is equal to V dt. Raise your hand if you know where this came from. Cool. So now I can integrate. Dr is the integral of V, which is V is V0 minus Gey times t dt, and let me put the initial, the boundary conditions, going from 0 to any time t, and R going, what is my initial position vector R0? What is the initial position vector of the particle? R0, what is it equal to? So it's the position vector. What is the position vector? It's the vector from the origin to the position of the particle initially, if you want the initial position vector. So initially, where's the particle located? At the origin. So what is the position vector of the particle initially? 0. Is that the 0 vector or the 0 scalar? Vector. Cool. 0 vector, and then R as a function of time. Okay, so I'll get R of t is equal to the integral of V0. V0 is a constant, so V0 t minus the integral of minus Gey t, that's, these are constants, and the integral of t is t squared over 2. And that's it. That's R as a function of time. Does that make sense? Questions? So you could have gotten, instead of getting R as a function of time this way, you could have gotten R as a function of time by solving for x as a function of time. Oops. And y as a function of time by just solving these scalar differential equations. You can double check and you should get the same answers if you integrate these versus integrating the initial vector equation. Okay? Now let's change this problem a little bit and add drag. Okay, so we're going to have projectile motion, but we're going to add a drag force. The drag force is going to be proportional to the velocity or to the speed, and it's going to point opposite to the velocity. So what is the magnitude of this vector? Show me with your fingers. Is it a 0? Is it a 1? Is it something else? It's 1, right? It's a unit vector because what we've taken is the velocity divided by its magnitude. We'll get a unit vector. Now it's opposite to the direction of the velocity because it's multiplied by minus 1. So that's a unit vector opposite to the direction of the velocity. So that's a drag force that's proportional to the magnitude of the velocity pointing opposite to the direction of the velocity. So I'll draw it this way maybe. And I still have the weight acting on the particle. Now if I want to solve for the motion of the particle, what do? If I'm going to get the equation of motion to be able to solve for the motion, what do I do? Yes? Before that, before I do any projections, I set up my problem. I have my bases, they're the same here as they are there. And I've drawn my free body diagram, I've expressed the forces. What's the next step to finding the equation of motion? Before writing the scalar components of the balance law, we need to write the balance law, right? We need to write the balance law. Newton's second law, or earlier first law, the balance of linear momentum. F equals ma. And before I do any projections, I will write the full vector equation of the balance law. And that's very important. So I'll do C mg/ey. That's the way. Now for the drag force, these two terms cancel out, and I'll get minus c times v is equal to ma. That's my balance law, right? It's a vector equation in how many dimensions? 2, x and y. So how many scalar equations can I get out of it? 2. Go ahead and get those equations, please. Quickly, this should take a minute. You already have your expressions for v and for a. Have you gotten the equations? What are you waiting for? Please do not do that.
Is it okay if I just like rewrite it? It's just like rewriting it right under it.
No, because we won't be using Cartesian coordinates all the time. Like next week we're learning about new bases, so that's not gonna work. Right, but you already have, well, v is a vector and v is a vector.
Oh wait, yeah.
Okay, and then you already have.
Oh, I could just put it.
Yeah, this is not quite right. You have a scalar on this side and a vector on the other side, and you cannot equate vectors and scalars. So not quite right. I want scalar equations, not vector equations. Something's wrong. Close, close. You're missing something. shoot.